All right, let's just dive right into this explainer, because we're exploring a truly mind-bending frontier today. We're looking at a project where programmers are attempting to codify the fundamental laws of the universe using something called the Lean theorem prover. Now, for those who might be new to it, Lean is a programming language and interactive theorem prover that's usually reserved for pure mathematics. But today, we're exploring a set of files that show an ambitious, almost crazy attempt to translate the messy, complex reality of quantum mechanics and astrophysics into absolute, undeniable mathematical code. To really wrap your head around the scale of this, think of normal programming as building a high-powered calculator. Something designed to just crunch numbers or run an app. Lean is entirely different. Lean is basically like building an infallible lie detector for the laws of physics. It doesn't just calculate things. It verifies if a conceptual statement is absolutely, undeniably true across all of reality.
At first glance, this just looks like standard open source directory architecture, right? You've got your open source folder, a Gnosis project, some work trees, and a directory with the intriguing name fork race fold theorems. But hidden within this exact digital location is where the secrets of the universe are literally being mapped into code. It's just a quiet, unassuming repository of .lean files that are actively trying to bridge the gap between abstract computer logic and the physical cosmos. There is something incredibly fascinating about the fact that the fundamental truths of our physical reality are being meticulously structured inside the exact same kind of folder systems you or I would use to organize a weekend coding project.
So looking at this repository really forces us to ask the ultimate question. Can we actually mathematically prove the mechanics of a black hole? I mean, we're totally used to scientists observing black holes through massive telescopes, or theoretical physicists passionately writing out pages of complex equations on chalkboards. But a theorem prover like Lean? It requires absolute, uncompromising logical perfection. It doesn't do approximations, it requires you to build every single concept from the ground up, until the computer agrees that your logic is flawless. So, to ask a computer to verify a black hole means we can't just plug in some gravity formulas and call it a day. We have to define exactly what information, gravity, space, and energy actually are at the most fundamental microscopic level. Only then can the computer agree that a black hole can exist within its digital universe.
And the 4 files we're looking at today act as our inventory for this journey. They represent a staggeringly ambitious attempt to formalize quantum mechanics and astrophysics. We're going to examine each of these files, derived directly from the source repository, to understand exactly what the programmers behind this project are trying to achieve. It's a journey that scales all the way from the tiniest imaginable building blocks of reality right up to the cosmic monsters lurking at the center of galaxies.
Here's our roadmap to take us from the micro to the macro. We've got Section 1, the Quantum Information Sandbox. Section 2, Landauer, Information meets Thermodynamics. Section 3, Braiding Black Hole Physics. And finally, Section 4, the Black Hole Paradox.
Let's move right into Section 1, the Quantum Information Sandbox. Let's see how this builds our foundation in the quantum realm.
This file, quantuminfosandbox.lean, acts as our safe experimental space where the very foundational logic of quantum information is being tested and mathematically proven. In a standard software environment, a sandbox is just an isolated space to safely test your code without crashing the whole system, right? Well, here, the code is quantum logic. Before you can even begin to prove a black hole, you literally have to formally prove a qubit. And just think about how difficult that is. In quantum mechanics, a qubit can represent a 1 and a 0 at the exact same time, a state we know as superposition. This is notoriously hard for human brains to intuitively grasp, let alone formally teach to a computer that is fundamentally built on strict, binary, true or false logic. You have to formally define quantum states, entanglement, and logic gates so that the Lean theorem prover understands these bizarre baseline rules of the universe. It's the digital equivalent of laying down the microscopic bricks that will eventually build a massive cosmic house.
Next up is Section 2, Landauer. This is where information actually meets thermodynamics.
Okay, so the absolutely crucial point here is understanding Landauer's principle, which explains why writing a math proof for Landauer Information Physics.lean is so groundbreaking. Rolf Landauer figured out way back in 1961 that information is inherently physical. Ever wonder why your laptop or your phone gets incredibly hot when it's processing a lot of data? It's actually not just a hardware inefficiency. You literally cannot delete data without paying a physical price in energy. Erasing a single bit of data releases a tiny, calculable, inescapable amount of heat. By actually coding this exact principle into their Lean theorems, these programmers aren't just doing abstract math anymore. They're forcefully binding their digital logic directly to the unyielding laws of thermodynamics.
If we compare these side by side, we see a really stark contrast between abstract math and physical reality, and this is exactly the gap the lean file is trying to bridge. On one hand, abstract pure math assumes you can calculate forever, for free. You can add and subtract into infinity without breaking a sweat. But physical reality demands a toll. The moment you introduce Landauer's principle into a strict theorem prover, you are forcing the computer to recognize that the information it is processing has weight, it has presence, and it leaves a real thermodynamic footprint. It's just a massive leap forward in making this formal logic mirror the actual tangible universe we live in.
All right, let's dive into Section 3, Braiding Black Hole Physics. We are pushing out to the absolute macro scale now.
We're juxtaposing the micro against the macro here to really show how the Gnosis repository scales its formalization efforts. We have completely left the subatomic safety of the quantum sandbox behind. Now, the repository takes all those fundamental rules about quantum logic and thermodynamic heat and throws them into the most extreme, hostile environment imaginable, the crushing, inescapable gravitational well and complex topology of a black hole.
The fact that they are attempting to codify the braiding of black hole mechanics into a single .lean math file is just absolutely staggering. Notice the slight directory change too? This file is housed in the gnosis-math/gnosis directory. Now, braiding in advanced physics is a highly technical concept. Think of topological braiding like actually tying intricate knots in the very fabric of space and time. It refers to the complex topological interactions of particles, or in this incredibly macro context, the twisted, chaotic space-time dynamics swirling around the event horizon of a black hole. To formally code this means breaking down that chaotic, swirling mathematics of space-time curvature into discrete, logical, undeniable steps that a computer can formally verify as definitively true or false. The ambition here is just breathtaking.
Finally, we reach the climax of our repository tour with Section 4, the black hole paradox. This is where the laws of physics seem to break down entirely.
This specific file, blackhole-information-sketch.lean, is an attempt to mathematically formalize one of the biggest, most hotly debated mysteries in all of modern physics, the black hole information paradox. And I love that the file name specifically includes the word sketch. It's such a great, humanizing detail, isn't it? It implies that even these advanced programmers, armed with strict logical provers, know they are treading on the very absolute edge of human understanding. They're outlining or sketching the boundaries of a problem that has completely stumped the greatest theoretical physicist on Earth for decades.
If we break down the sketch into steps, we can really see the building sense of awe, as the paradox mathematically asks if the universe just permanently deleted information. Step 1 is simple. Throw a physical book into a black hole. The information contained in that book securely enters. Step 2. Stephen Hawking famously proved that black holes are not entirely black. They slowly leak energy over trillions of years and will eventually evaporate completely into nothingness. But Step 3. Step 3 is the kicker. If the black hole is entirely gone and the radiation left behind is just featureless random static, where did the information from the book actually go? Remember Landauer's principle from earlier. You cannot just delete physical information without a trace. If the universe permanently destroyed that data, it completely breaks the core, foundational laws of quantum mechanics. It means reality itself is fundamentally broken. And right now, somewhere in a .lean file, a programmer is trying to make a computer mathematically solve this exact contradiction.
So as we wrap up this explainer, we really have to wonder, what other impossible physics are these programmers quietly turning into undeniable mathematical code right now? We started with a simple everyday file path string and ended up staring directly into the mathematical void of an evaporating black hole. This project to formalize the universe piece by piece is quietly happening right now in open source directories, literally bridging the gap between computer code and cosmic reality. So I'll leave you with this to think about. If you can perfectly code the rules of the universe into a theorem prover, at what point does the digital simulation become entirely indistinguishable from the physical reality?